Okay, so at GCSE, in fact, at Key Stage 3, you do first start learning about what are turning effects. And the idea that what you might have first got is a picture of people on a seesaw. So in fact, there's quite a good animation or simulation that you can use for this. So I'll briefly get that up so you know what I'm talking about. So if we go to Balance Lab, and we've got these blocks that we can turn on and off, but we'll leave them on for now. And what we do is we place. If we start off by just placing a 10 kilo. Let's say the challenge is you got two 10 kilo masses to place, and then what you got to balance it. Most people will know, well, just place it the same distance from the pivot. When you turn it off, it's balanced. Whereas if I took it from a different point, it's not going to balance. Okay, move that one in now. It should balance like that. So you can play around with this and make sense of it. You've got we can use our rulers to actually measure the distance. They're the same distance from the pivot, and they're the same mass. The challenge will come when we're trying to balance two masses that aren't the same. So let's say we've got a 10 kilo and a 20 kilo. So I'm just going to place that down anywhere now. And where do you think you would have to balance? Where do you think you would have to place these in order for it to balance? Absolutely right. The 20 kilo will need to be closer. Now, but we want to do a bit better than that. Let's say that one's at 2 kilos. Where would the 20 kilos be placed? Right, around 1. Let's see. Yeah. So what we've done is when we doubled the distance, we also halved the mass. So when we're increasing the distance, we're increasing what we call the turning effect. How much of an effect it makes on turning the seesaw, turning the lever. So if I take that off and put this away, and take that away like that. Well, if I want, basically, the reason why it's called a turning effect is that if I'm trying to turn a seesaw, I place it there. You can see it turns it, but only slowly, right? I could take it off. If I put something much heavier in that same place, it turns it a little bit more easily. So it has a bigger turning effect. A larger mass will cause a larger weight, so a larger force. So it has a larger turning effect. As well as changing the size of the force, I could also change the distance from the pivot, like that, and that also has a greater turning effect. So the turning effect will increase if the distance from the pivot is greater or if the force is greater. And in fact, you can. I guess the definition of turning effect would be how much of an effect on the turning does it have? But you don't usually get that question in that way. It's more. So we'll look at. Okay, so basically, to balance something, we're just looking at balancing at the moment. I've got a turning effect of essentially 1 times 10. So you'd work out the turning effect by multiplying the distance by the mass, and then to balance, that's a clockwise turning effect. We're rotating it clockwise with this mass here. When I place that there, I'm rotating it clockwise. Now I could take another 10 kilograms and place that there, and then rotate it anti-clockwise. Now the turning effects, the anti-clockwise and the clockwise turning effects are equal, and so that the seesaw is balanced. If I change the distance, then it's no longer balanced. The turning effect, the anti-clockwise turning effect, is greater than the clockwise turning effect, and so it rotates clockwise. Likewise, I could increase the mass, but keep the distance the same. And again, it's not balanced because the turning effects aren't balanced. So you don't need to keep the distance and the force the same. You just need to keep the product of the distance multiplied by the force the same. So, which is what we did earlier on. So we got the 20 kilos and we placed that at 2 meters. Oops, all the way around. Place the 20 kilos at 1 meter and the 10 kilos at 2 meters. And now they are balanced because 1 times 20 is the same as 2 times 10. Okay? Okay. So let me just take a snapshot of that. So a turning effect or a moment is how effective a force is at turning something or rotating something. In other words, let's go up to this one over here, and we'll say that I'm trying to turn this this bolt here. Now, so what I could do is I could get a spanner and I can increase the size of the force, or I could get a longer spanner and increase the size of the distance from the pivot. And it is how effective is my force at turning that pivot is down to how big the force is or how big the lever is. So the turning effect, otherwise known as the moment, is equal to the force multiplied by the distance. Now, that is not the complete formula. I'm going to correct that in a moment. But for now, let's just understand it as the force times the distance, okay? So if I increase the force, I'm going to increase the moment or the turning effect. And if I increase the distance from the pivot, this is the pivot here, the thing that things are pivoting on, then that would also increase the turning effect. So really I should probably just write distance from pivot.
Wait, so the pivot is the thing that's turned.
The pivot is the point at which the thing is at which the turning occurs. So the thing that's actually turning is, well, everything's turning when, the lever's turning, it's all turning. It's turning around this pivot. The pivot is the point at which things are turning about. So the pivot is the only thing that's not moving, I suppose. That's staying, and then everything else is moving around it. Now, the difference being is that this force or this distance, they have to be perpendicular to each other. And if they're not, then you have to take the components. So a while ago, we looked at taking components of forces. If we look on this one on the right, this is the size of the force. Let's say the size is, 5 newtons. We don't do 5, and let's say the distance is, 10 centimeters. We don't do 10 times 5 times 10. We would have to work out the component of this here. So this theta 1, this is going to be equal to 5 cos theta 1. Okay, briefly, just to explain how I got to that point. I just need to draw a triangle. So this is the force. This is the angle. That's a right angle there. And this would be my adjacent. And that's my hypotenuse. The adjacent is equal to, the adjacent is equal to hypotenuse multiplied by cos theta, because cos theta is equal to adjacent over hypotenuse. So the perpendicular component of this force is 5 cos theta in this case. One more point about this unit. If I did 5 times 10, then the unit, if this was perpendicular anyway, the unit would be Newton centimeters. Technically, the standard unit for moment is going to be Newton meters, but it does, as long as you're consistent with your units, then you won't have any problems. In other words, as long as you know which units you're referring to, then there won't be any problems. So if you want the unit in Newton meters, make sure you have the distance in meters. If you end up measuring the distance in centimeters, the moment's going to be in Newton centimeters. Another thing to mention at this point is that when you do the topic on energy, you'll find out that work is also equal to a force times a distance. Whereas the force is measured in newtons and the distance is measured in meters. And so you could measure work in Newton meters as well, but we don't. We measure the work in joules because it's the amount of energy that was used usefully. So we tend to do that. And so what some people might think is, well, does that not mean then I can measure moment in joules? Can you do that? The answer is no, you cannot, because a moment is not energy. So despite the fact that you can use, it looks like they're transferable, they are not, because a moment is not an energy. It is how effective a turn is, how effective it is to actually, how effective is your force on turning something, and work is a measure of energy. Okay, so that's the basics of what moments are, or turning effects, and it comes into play when we look at center of mass as well. But we'll stop the video at that point.